All right, so thanks everyone for being here. Today is at the Autonomy Talk, there's Andrea Zanelli as speaker. Briefly about his bio, Andrea Zanelli received a bachelor degree in automation engineering from Politecnico di Milano, and he has a master's degree in robotic systems and control from ETH Zurich. He pursued then a PhD at the System Control and Optimization Laboratory at the University of Freiburg in Germany. And since 2021, he is a postdoctoral researcher at the Institute for Dynamic Systems and Control at ETH Zurich in Professor Zeilinger's group. His research focuses on the development and software implementation of efficient numerical methods for embedded optimization and nonlinear model predictive control with numerical and system theoretic guarantees. So with no further ado, the stage is yours.
Yeah, thanks a lot for the introduction, and thanks to both Alessandro and Joelle for organizing this. I'm glad to be speaking today. And thanks everybody for joining, of course. I'm going to talk about efficient, inexact numerical methods for model predictive control with feasibility guarantees and applications of these to autonomous racing. So I'm going to start with a bit of motivation about MPC or model predictive control. And throughout the entire talk, we will be concerned with the design of a feedback control system, where our system is depicted in this block here. And the state of the system is denoted by X, and our task will be the one of designing a controller that will use the knowledge of the state X in order to compute an input U that can be used to steer the system, for example, to an equilibrium or to track a certain trajectory. And we're going to do this using MPC. And the main idea behind MPC is the one of exploiting a model of the dynamical system that we would like to control in order to optimize over predicted trajectories. So we will be optimizing over input sequences. And once we have computed an optimal solution that minimizes a certain cost function, we will apply the first control move in the optimal sequence, let the system evolve, and once we get a new measurement, we reformulate an optimization problem and apply this mechanism in a recursive fashion. So the resulting control strategy has several advantages, ranging from the fact that we can handle constraints and multivariate problems, as well as nonlinear problems. And it also leads to the behavior of the closed loop system, which approaches the optimal desired behavior. Okay, so for these reasons, MPC has been applied to a wide range of applications, going from certain fields in the process industry, where it became the state of the art already in the late 70s. And much more recently, it's becoming a viable approach for faster dynamical systems. And just to name a few, this could be applied to wind turbines, combustion engines, or autonomous cars. Okay, and although a considerable progress has been made over the last, say, 1 to 2 decades, the main challenge to some extent still remains the computational burden associated with MPC. And this stems from the fact that at every sampling time, we have to solve a non-convex program of this form, where X is a parameter that denotes the state of the system. And what we do is to predict ahead the behavior of the system using our model, which is described by this function psi. And as we predict the behavior of the system, we want to satisfy these constraints denoted by pi, and for the terminal state, pi n. Okay, so this defines the feasible set of our optimization problem, and we want to find a point inside this feasible set, which also minimizes, at least locally, our cost function. So we will have to do this for every sampling instance. And it's not hard to believe that this is somewhat computationally challenging, especially if the problem is a large problem or is highly nonlinear and non-convex. So what we're going to do is to seek for approximate policies that are cheaper to compute And as we do this, the question naturally arises of whether we can preserve certain algorithmic and system theoretic properties of the resulting approach. And this is exactly the main topic of today's talk. I'm going to present a few inexact methods for NMPC that preserve these kind of guarantees. This is the outline of the talk. It will be structured in 3 parts. In the first part, I'm going to talk about zero-order NMPC and anytime feasible SQP. Here, the idea will be to construct a method that can be early terminated at any point and will provide a feasible solution that we can use for control purposes. The second part will revolve around an application of this method to autonomous racing. And in a third part, I'll be talking about inexact methods for robust MPC that can be used to speed up the computations associated with robust optimization. Okay, so let's get started with the first part of the talk on zero-order methods for NMPC. And in particular, we will be interested in solving our NMPC problem, which I have reformulated here in compact form with sequential quadratic programming, or SQP in short. As we do this, at every iteration, we will have to build a local quadratic approximation to our NLP, where K denotes the iteration index. And at every iteration, we will have to evaluate the derivatives of the functions involved in the definition of our NLP on the left, and to evaluate the constraints, okay? And our task will be the one of reducing the cost associated with the solution of these problems. And in particular, we are interested in reducing the footprint associated with expensive linear algebra operations, such as matrix multiplications and factorizations, and recomputing the derivatives. So these red quantities in the QP subproblems. And to do this, we're going to leverage a simple and yet far-reaching idea, which is the one of freezing the sensitivities across QC subproblems. And this is definitely not a new idea. It's actually related to second-order corrections, which were introduced already in the 80s in the context of nonlinear programming by Fletcher. And in this context, we're going to use the wording zero order because the subproblems that we have to solve do not exploit any knowledge of the first-order derivatives of our functions f, g, and h, but they will only involve evaluation of the zeroth order derivative of the functions involved in the NLP. Okay, so I will try to convince you to some extent that this can be used to speed up the computations considerably, in the sense that we don't need to evaluate these derivatives across subproblems, and that also by fixing these red quantities here, we can obtain a cheap solution to the QP subproblems. Okay, so first of all, a few properties of the resulting algorithm. If convergence is achieved, we can prove that the solution obtained will be an approximate solution that satisfies the constraints. And I'm going to call this solution y tilde. And an interpretation of this approximate solution is that it solves a perturbed problem, which pretty much looks like the regional problem, where we have f, g, and h, plus a perturbation in the objective. Okay, and this perturbation is a function of the solution itself, and it will be proportional to the deviation between the fixed Jacobians that we're using in the QP subproblems and the true Jacobian of our functions, as well. It will be proportional to the multipliers. And this holds for both the equality constraints and the inequality constraints. Okay, so this will recover a feasible solution, which is, however, not locally optimal. And I'm not going to talk about too much about system theoretic considerations, but for those of you who are interested, we can also show that the resulting feedback policy is locally stabilizing, and you can find these considerations in these two references. Okay, so we have now a way of computing a feasible approximate solution to our NLPs, but we can go one step beyond that. And after convergence, we can relinearize and repeat the whole process. And this is going to define the outer iterations of our feasible SQP method. So the idea now is that if we carry out these inner iterations with fixed sensitivities, we can get a feasible solution. And that means that we can terminate the outer iterations at any point and still have a feasible solution that we can use for control purposes without violating the constraints. Okay, so the algorithm looks like this. We have a primal dual guess, where I denote with the hat superscript the linearization point. In the outer loop, we're going to update these sensitivities. So basically the red quantities in the QP problems. And in the inner loop, we evaluate only 0th order information. So that means we're only evaluating G and H. We solve the resulting QP and update the approximate solution. And after having computed a feasible solution, we can, if we still have CPU time, we can update the derivatives. Okay, so this leads to a feasible SQP strategy that we can terminate at any point, basically. A few properties of the two loops when it comes to the inner iterations, so the ones with fixed sensitivities, under some relatively standard assumptions, we can prove Q-linear convergence of the iterates in the primal dual space. And the assumptions that we have to make, loosely speaking, are strong regularity in the sense of Robinson, together with the fact that the Jacobian approximation is sufficiently good. And for those of you who are familiar with Newton type methods, this is equivalent to a kappa condition. And for what concerns the outer iterations, we again make some relatively standard assumptions. Namely, we assume that linear independence constraint qualification holds together with sufficient second order optimality conditions. And this guarantees that we obtain Q quadratic convergence of the outer loop. Okay, so this defines the key properties of our feasible SQP algorithm. And I would like to talk about an illustrative example. So we're looking at this two-dimensional non-convex program where we are minimizing this nonlinearly squares cost, where alpha is just a tuning parameter for illustrative purposes. And we want to minimize this cost while satisfying this equality constraint on Y1 and Y2. And in particular, this constraint defines this black manifold in the primal space. So here we have in black the feasible set. These lines are the contour lines of the objective, and the optimal solution is somewhere here. And we apply two methods: the proposed feasible SQP, whose iterates are in blue, and a more standard SQP algorithm that uses a Gauss-Newton Hessian approximation. And here I'm plotting just the outer iterations, of course, and we see that they're all feasible and they make progress towards the optimal solution somewhere here. The same doesn't hold, of course, for a standard Newton or SQP method like the Gauss-Newton method. And we see that the iterates only become feasible in the limit as we converge to the optimal solution. So this basically verifies our observation that the outer iterates should be always feasible. And a second observation that we can make is that indeed the iterates are converging Q quadratically in the primal dual space. So here we're plotting the norm of the primal dual step over iterations. And we see that in blue, we have the behavior of the zero order SQP algorithm, which converges quadratically rather quickly, and Gauss-Newton is only converging linearly. So this also validates our theoretical results on the contraction rate. So when it comes to software, the first thing that we have to keep in mind is that we shouldn't be solving the QPs with any QP solver, but there are QP solvers that are more suitable for this application. And in particular, since we're fixing the matrices in the QP subproblems, we should be using an active set QP solver such that we can resort to cheap computations when we're solving the QP subproblems. So we have implemented the method in two software frameworks, and the first one is Akados, and it's an MPC specific dense solver using QP Oasis. And we also have an implementation which is publicly available on GitHub of a general purpose sparse solver, again using QP Oasis. I'm now going to talk about a benchmark of the performance associated with the first implementation, and then we will see how the implementation of this solver can be used for an application in miniature autonomous racing. So first, the benchmark in Akados. So we have implemented the feasible SQP method in this software framework, and we're benchmarking this on a control task, which is the one of stabilizing this nonlinear hanging chain to its rest position depicted in gray here. So the system is basically composed of a series of masses connected by springs, and one end of the chain is attached to a wall here, and we're actuating the other end, and we want to steer it back to its rest position without hitting this wall on the side, which is going to define a state constraint, basically. And we picked this example simply because we can easily scale up the number of states and observe the computational complexity of the benchmark methods. So we have different scenarios here with index 0 to 8, where we increase the prediction horizon in the MPC problems, as well as the number of states. So we're adding masses to the chain, and the accuracy of the integrator, which is going to result in a larger and larger problem. And on the right, we see the CPU time in milliseconds associated with the different scenarios. And we see that the proposed algorithm that uses fixed sensitivities is always faster. And it can also achieve a pretty large speed up for some of the instances. So here we're about 20 times faster than standard vanilla SQP algorithm, where we update the sensitivities across iterations. And of course, as we are approximating the feedback policy, this is not going to lead to optimal behavior. And so we're evaluating the relative suboptimality by kind of integrating the stage cost for the entire duration of the simulation. And this is quite small. So this resulted into a relative suboptimality of 0.1% for this benchmark. So the take-home message should be that we're able to speed up quite considerably the computations associated with MPC using this approximate computations. Okay, so this concludes the first part of the talk, and I'm now going to talk about an application of this feasible SQP method to autonomous racing. And this is joint work together with Logan Numerov and Andrea Carron. So we're now looking at the task of controlling this system depicted in the picture. We're talking about miniature racing cars of type Kyosho Mini Z, and the collaborative robotic system, which is a platform that has been developed by Andrea Carron, provides a Vicon motion capture system that we can use to accurately measure the position of the vehicles. And what we would like to do is to be able to compute the input to be provided to the system within 30 milliseconds and to safely drive the miniature car around in the racing platform. Okay, so computation of a locally optimal solution can be CPU intensive in this context. And so what we often do is to approximate the solutions. And this can be done, for example, by means of early termination. However, if we're not using a feasible SQP method, this is not going to guarantee that we satisfy the constraints, which is somewhat critical, especially for automotive or aerospace applications. And so what we would like to do is to apply our anytime feasible SQP that can be early terminated while guaranteeing state and input constraint satisfaction. And the main idea that we exploited is to design an MPC problem such that a feasible candidate is always available. And we will see that this is related to terminal ingredients design. And to use any number of iterations of feasible SQP in order to improve our feasible candidate. A few words about the model that we're using to design the MPC controller. So we have a bicycle model of the vehicle with 6 states, and we have this red quantities defining some parameters of the dynamics, and we use a Pacheco friction model to model the forces applied to the tires. And the main thing that we should be careful about is that our model is uncertain in the sense that, for example, among other things, we don't know a very good model for the friction forces. And so that means that the dynamics are not only affected by the current state of the system and the input that is being applied to the system, but the next state, X plus, will also be determined by a disturbance. And for this reason, we need to account for uncertainty in some way. So for this application, we decided to rely on an inherently robust MPC formulation following the framework presented in Allen et al. From 2017. So we will be solving MPC formulations of this form, where with respect to the standard formulation that I have introduced before in the talk, we are slacking the constraints to allow for small deviations or small violations of the constraints, okay? So this quantity Xi is going to be positive and highly penalized. And what the solver is going to do is to find a feasible solution if it exists. Otherwise, it's going to allow for small violations of the state constraints. Okay, and this is somewhat our best option when we are using inherent robust MPC. So we're going to guarantee recursive feasibility plus a violation of the constraints, which is somewhat proportional to the model mismatch. So that means if we have a better and better model, we can guarantee that the constraint violations will be smaller and smaller. And finally, in our cost term L, we're going to use an MPCC or contouring cost. This is also kind of a popular formulation in the context of MPC for racing and autonomous driving. And the main idea is that we have a few parameters that allow one to trade off progress for deviation from the center line and to kind of tune the behavior of the resulting controller. Okay, so as I mentioned before, in order to guarantee recursive feasibility, the key thing to do is to design terminal ingredients. And in particular, we'll have to design the terminal set XF to be positive invariant. And we exploited a very simple idea, which is the one of relying on any feasible periodic trajectory and to set XF to be basically the one defined by this manifold. So at every instance, we predict to be on this manifold, and if we are on it, we have a way of staying on XF by applying the feasible input on the periodic trajectory. Now, the theory from the framework that we're using doesn't apply straightforwardly for those of you who are more familiar with MPC contents. However, an extension seems possible, and the main limitation lies in the fact that our terminal set doesn't have an interior, which is a rather technical assumption, but it seems that applying some results from recent papers, we can extend the theory, and nonetheless, this works quite well in practice. And here we have some simulation results. So we're applying the feasible SQP method with a single outer iteration. So we're not computing locally optimal solutions, but only feasible solutions. And again, we carry out a single outer iteration, and this results in a computation time of 10 to 15 milliseconds. And the prediction horizon there that we're employing is n equal 30. So in blue here, we see the closed loop trajectory for 1.5 lap or so. And in red, we see the open loop prediction computed by the solver. Okay, so this seems to work quite well. We have some bounded model mismatch, which should somehow reflect the quality of our model. So we actually took the design and deployed on the physical system. And these are some preliminary experimental results. So we have exactly the same setting that we have in simulation. We're running the feasible SQP method with a single iteration in the outer loop, such that we always have a feasible solution. And this takes, again, around 10 to 15 milliseconds, which is short enough to be able to provide feedback within the 30 milliseconds available. Here we have a close-up that shows also quite some dynamical maneuvers. So this also concludes the second part of the talk, and I'm now going to present an approximate method for robust optimal planning and control. So a bit of motivation for the upcoming slides is that in the application that I've just described, we were controlling an uncertain system where, for example, the uncertainty could come from an inexact unknown tire model. And again, this means that the next state x plus will not only be determined by the current state x and the current input u, but also it will depend on the realization of the disturbance w, which lives inside a compact set w. Okay, and so that means that the next state is contained in a set, and we have here a nice visualization, which was produced by Feng Long, a student which I'm co-supervising with Andrea Caron. And here we see that for different realizations of W, the next state will be contained in this ellipsoids here. So what we want to do now is to take a more quantitative approach to robustness. Until now, we have relied on inherent robustness. And this basically means that our controller is going to work for sufficiently small realizations of the disturbances. And what we're going to do next is to rely on constraint tightening such that we can guarantee that our constraints will be feasible for most realizations in the disturbance set and potentially all of them. So we're going to focus on a specific parameterization of the uncertainty, and this is the one of ellipsoidal uncertainty. So we're going to assume that W lives in a set which is an ellipsoid defined by this positive semi-definite matrix W. And the goal will be the one of designing efficient algorithms that can be run in real time, because we would like to solve the Robustified NMPC problems as fast as possible in order to provide feedback, and to leverage constraint tightening such that the constraints will be satisfied for all the realizations of the disturbances, or at least for a very large number of the realizations. So in order to do this, we're going to rely on this idea, which stems from the PhD thesis of Boris Huska. And it boils down to approximating the reachable sets with ellipsoids. So for each x and u, we're going to assume that for all the possible realizations of w inside this ellipsoid, the next state defined by psi of x, u, and w will also be in an ellipsoid defined by this PSD matrix sigma plus and centered around the nominal evolution of the system. Okay, so what we need is a tool that, given the current reachable set, is able to compute an approximation of sigma plus at the next time step. And the main tool that was proposed in this PhD thesis by Boris Huska is the one of Lyapunov ODEs that can be used to propagate the approximate reachable sets. And so here we have an update that takes into account the current reachable set and disturbance uncertainty set, and it computes the approximate reachable set defined by sigma plus, and this is done using this linearized dynamics. Okay, so once we have this approximate reachable sets, what we're going to do is to tighten the constraints such that they will be satisfied for a vast majority of the scenarios. And this is in contrast to what we've been doing before with the inherently robust MPC formulation, where we used instead soft constraints. So it's important to stress that this Lyapunov ODE or discretized Lyapunov ODE doesn't provide an outer approximation to the reachable sets, but only an approximation of them. However, by adding a nonlinear term, what I'm going to be presenting can be extended to a setting where sigma plus actually defines a true outer bounding approximation of the reachable sets and can be used for exact robustification of the constraints. Now, all of this seems quite nice. However, if we apply vanilla numerical methods to the resulting MPC problems, this becomes computationally prohibitive. And for moderate state dimensions, this will be up to 2 orders of magnitudes lower, as we are going to see in a few slides. And in order to understand where this computational bottleneck comes from, we can look at the resulting robust MPC formulation. So here we basically have kind of the same MPC formulation we had throughout the entire talk, but additionally we have this dynamics for the ellipsoidal reachable sets. So these are basically the discretized Lyapunov ODE. And we additionally use this sigma quantities inside the constraints in order to compute the robustification. And this constraint tightening term is based on the support of the ellipsoidal reachable sets. So what happens is that our state is effectively inflated. And if we started with a system to be controlled with NX states, we're now left with a much larger state space. And in particular, due to the introduction of the ellipsoids, we're now dealing with NX to the second power. And if we apply vanilla methods to solve this numerically, this leads to a complexity that scales with the 6th power of NX, which is of course quite unfortunate. So what we would like to do is to reduce this computational footprint associated with robustified MPC problems. And we're going to do this by introducing the zero-order robust optimization algorithm, or ZORO in short. In order to introduce the algorithm, I'm going to rewrite the robust MPC problem in compact form. So here we have just lumped the cost terms into F, the non-robustified inequalities and equalities into G and H respectively. This equality here is summarizing the discretized Lyapunov ODE. And finally, we have the robustified constraints where we use the support of our ellipsoids. We additionally introduced this scalar term sigma, which is scaling the uncertainty present in the Robustified NLP, and in particular, this will be proportional to sigma bar, the amount of uncertainty in our initial state, and the W's, which kind of quantifies the amount of uncertainty being injected into the system at each time stamp. Okay, so we have this parameter here, and the interpretation of this Robustified NLP is that this equality implicitly defines an ellipsoid, and we're going to robustify the constraints using the support of this ellipsoid in the direction of the affine constraints. Okay, so the ZORO algorithm will be exploiting a sequential quadratic programming strategy. So we're again applying the same type of algorithm that I've been talking about in the first and the second part of the talk. And to do this, we're linearizing the equality and inequality constraints and also building a quadratic objective of this form. And in particular, we're going to focus on the linearized Lyapunov dynamics, which take this form. And since they are a function of y and p, of course, the linearization will be coupling the two terms in delta y and delta p. And this is somewhat the main source of complexity, because we have now to jointly optimize over y and p, which in our Robustified NPC problem would be corresponding to the state and input trajectories and the sigma trajectories, respectively. So we're going to try to reduce the computational footprint by imposing a specific structure on the QPISA problems. And we can do this by zeroing out the Jacobians that multiply delta y. Okay, and so this is somewhat similar to the ideas that we were using in the feasible SQP method, because we are approximating first order information in the QPISA problems, and this qualifies the algorithm as a zero order method, which gives the name to the ZORO algorithm. Okay, so if we zero out these quantities here, we basically have not anymore an exact linearization of the constraints, but an approximate linearization. And this approximate linearization reads like this. So it's phi lin tilde, where we have eliminated the terms in delta y. So these two red quantities, basically. And after doing this, we're able to eliminate delta p in this form. Okay, so if we set this expression equal to 0, we're able to compute an expression for delta p. And by replacing delta p in the original SQPISA problems, we're left with a much smaller problem where we're now optimizing over delta y only. Okay, so this is for a general Robustified NLP. And I would like to make it a bit more specific for MPC, such that it's probably easier to understand what is going on. So for MPC, the ZORO algorithm boils down to the following steps. We start with a primal guess, that being a guess for the ellipsoid trajectories and for the state and input trajectories. We compute the tightenings. So these are basically the supports of the ellipsoids defined by the fixed sigma trajectory. After computing these tightenings, we linearize and solve a nominal equivalent problem, which is going to be much smaller because it's not going to involve optimization over the sigma quantities. And this will provide an update for the state and input trajectories. After having computed the updated state and input trajectories, we update the sigma quantities with the Lyapunov propagation. So this is basically a forward simulation of the Lyapunov dynamics. And after doing this, we repeat until convergence. Okay, so what we obtain as an output is a suboptimal but feasible solution to our Robustified NLP. And again, in summary, what we have to do is a forward propagation of the Lyapunov dynamics plus the solution of a nominal MPC problem. And we know this from standard results that if you apply, for example, interior point method to the solution of this nominal MPC problem, the complexity will decrease from nx to the 6th power to nx to the 3rd power. And this is, of course, quite beneficial from a computational point of view. So a few properties of the resulting algorithm. We cannot guarantee that this will converge to the optimal solution or a locally optimal solution. However, if convergence is achieved, it will converge to an approximate but feasible solution. And when I say feasible, I mean it will be satisfying the constraints that we specified in our robust optimization problem. We can show that the deviation of the suboptimal solution from a locally optimal one will grow as a big O of sigma, where sigma denoted the amount of uncertainty in our optimization problem. And we can also show that if the quantity sigma is moderate, so our uncertainty is not too large, the iterates will converge q-linearly in a primal dual space to a feasible solution. Okay, so we basically designed an algorithm that is capable of computing a solution which is not locally optimal anymore, but it will satisfy our robustified constraints. So let's now look at some benchmarking of the proposed method. And again, we're going to look at the nonlinear hanging chain problem, again, just for the fact that we can easily increase the state dimension and observe the asymptotic complexity of the two strategies. So the task is, again, the one of stabilizing the chain back to its rest position right next to this wall on its right. But in this case, the dynamics will be affected by uncertainty, and we'll have to account for that in some form. And in particular, we benchmark 3 different methods. The first one is nominal MPC, where we basically neglect the fact that uncertainty is going to affect the evolution of our dynamical system. The ZORO algorithm, which I have just introduced, and a standard robust algorithm that is not tailored to the structure of our MPC problems, and where again we use ellipsoidal uncertainty sets. And what we plot here is the distance to the wall in the y coordinate here. So if we have a negative distance, that means that we are hitting the wall and violating the constraints. And we see that violation happen quite often for the nominal MPC strategy, while the same amount of conservativeness is obtained for both the ZORO algorithm and the standard non-tailored robust MPC algorithm. Okay, so this kind of describes the closed loop behavior of the two strategies as opposed to nominal MPC. But even more interestingly, here we have the computation times associated with the 3 approaches. And in particular, for different number of masses, which means different number of states. For reference, 3 masses means that we have 9 states in the system, and 7 masses means that we have 21 states. And we see that the nominal MPC controller is, of course, requiring much less CPU time than the robust MPC controller in green. And we see that the ZORO algorithm is slightly more expensive than nominal MPC, but it's still 1 order of magnitude faster than robust MPC for the case where we have 9 states, and 3 orders of magnitude faster than the vanilla algorithm for the case where we have 21 states. So this speeds up the computations quite a bit, and we can actually witness the reduction in asymptotic complexity from nx to the 6th power, which is what we expected, to nx to the 3rd power with the approximate algorithm. Okay, so this actually concludes my talk. I have presented two numerical methods for MPC that can be used to dramatically speed up the computations associated with the solution of the underlying non-convex programs, while preserving key properties such as feasibility with respect to the constraints and stability of the closed loop. These two methods, namely, are the feasible SQP method that we can terminate at any point without violating the constraints, and the zero-order robust MPC algorithm. And I've also talked about an application of the feasible SQP method to autonomous racing. Ongoing research and things that we would like to address in the future are, for example, speeding up feasible SQP, the implementation of the feasible SQP method, in particular for the case where we have many active set changes across QP solutions. This can be quite demanding, and we're looking into ways of speeding up the iterations. A second thing that we're looking into is the application of the ZORO algorithm to the physical autonomous racing platform that we saw in the second part of the talk. And a third thing that we are investigating is an extension of the ZORO algorithm to more general Lyapunov ODEs that guarantee true outer approximations of the reachable sets as proposed in these references, such that we can guarantee that no constraint violation would be taking place. And yeah, with this, I would like to conclude my talk. Thanks for listening, and I'd be happy to take questions.
Thank you very much, Andrea, for the interesting talk. I think if someone has questions, he can just simply unmute himself and ask. So I'll start with one to break the ice if no one goes. So especially for the first method where you have where you manage to keep the problem always, you have this anytime property and you preserve feasibility. But also for the ZORO algorithm, let's say it seems that I would say it's always better with respect to the benchmark that you presented. Are there cases in which you would not advise to use it?
Yeah, so I think this is exactly one of the 3 points we're looking into at the moment. So in order to leverage the fact that the sensitivities are frozen across inner iterations, we cannot use any QP solver. And this is something I've mentioned. I hope at some point that we have to use active set methods. And these methods are not scaling very well with the number of active set changes across QP iterations. So if you have a problem with very many constraints with the current implementation, yeah, it might encounter some difficulties, I would say. So that's one of the difficulties that can be encountered, at least for feasible SQP.
Okay, I see. Thanks.
Hi, Andrea. I have a question. So when you're talking about zero order SQP or feasible SQP, but I noticed that you did not mention how do you get that M matrix? I mean the Haitian matrix, second order. How would you did you freeze that as well, or?
Yeah. So are you referring to feasible SQP or to ZORO or both? Sorry, I didn't catch that.
So in the first part of the talk, feasible SQP. So I remember that in each QP, yes, that M matrix. I'm asking about that M matrix.
Yeah. So I think this is actually the same quantity that appears in the derivations for the ZORO algorithm, and this has to be a sufficiently good approximation of the Hessian of the Lagrangian. It's kind of a standard assumption in Newton type method.
Yes. But my question is that did you update that in the outer loop or not? Or just you are maintaining the same?
So for the application that we saw in the second part of the talk on autonomous racing, we're actually using a Gauss-Newton approximation for the M matrix. So if you're familiar with that, if you're using a linearly square subjective in your MPC problem, you can take the gradients of the residuals and you can compute a Gauss-Newton approximation. And the idea is that if the residuals are sufficiently small, or jointly, let's say that the second order derivatives of the residuals are sufficiently small, then this can be a very good approximation to the Hessian of the Lagrangian. And on top of this is going to be positive semi-definite. So this is quite beneficial because inside the QPSA problems, we don't have to do any regularization. I hope this answers the question.
Yes, very much so. Thanks.
Okay, thank you.
All right. Anyone else? Last call for questions. All right, then I guess we can stop here. Thank you very much, Andrea. And thank you all for attending. Oh, wait, there's someone in the chat, maybe a question? No, okay. And I guess see you next week. Thank you.
All right, thanks a lot. Thanks a lot.
Bye-bye.
Have a nice evening.